Welcome to topic 5.4, orbital notation. The first thing I need you to do is print off this little road map, or if you don't have the ability to print, please get a piece of paper and, to the best of your ability, set this up following the same pattern. This is going to be our roadmap. It's going to be what helps us start with our next kind of big idea, which is an electron configuration. So take a moment and pause this video and fill out this sheet according to how I have it set up on the screen. So now that you have filled this out, this is again going to be a little bit of a handicap to start us out. So where we left off with the idea with the electron is that electrons are stored in energy levels, and there's more specifics to those energy levels. We do know that as you make your way out, those electrons have more energy. And then again, one other thing we looked at is that light can be emitted by an electron as it goes from the excited state to the ground state, and it can release it in different wavelengths, which correlates to different colors of light depending on the transition taking place. So what we're going to work on now is starting one piece of the pie when it comes to writing what's called electron configurations, which is basically like writing an address to where the electrons are stored. And we're going to work on this for the next week or so. So right now, this is going to not make a whole lot of sense, which is fine. We're going to need it for later on. But just make sure that you have 1 through 7. Make sure you have this whole column as S, P, D, F, and then just make sure that you have your arrows. Also write this in here, and if you didn't write in the start here at the top, please do that. And so the S can hold 2 electrons, P can hold 6, D can hold 10, and F can hold 14. Right now, this means nothing to you. We're going to work on it. Okay, so here's the actual notes. I'm going to do it through printed off pages today. It's going to help so I can reference that little cheat sheet here in a moment. So we've talked about electrons, and we have said that depending on the number of electrons the element has, they always start close to the nucleus and make their way out. So there are 3 rules that control where an electron will be found. So the first rule is named after Aufbau, and this is called the Aufbau principle. And essentially, electrons will always be found closest to the nucleus in that first energy level and make their way out. So again, if you have the option to maybe have an apartment on the first floor versus, say, the 6th floor, and the only thing you have are stairs and not an elevator, you are probably going to pick an apartment on the first floor versus the 6th floor. Electrons are that way. They don't want to have to make their way out further from the nucleus unless they have to, and that's essentially what Aufbau governs. The next rule that controls where electrons go is the Pauli exclusion principle. So this is where things start to get a little bit strange. So when we look at electrons and where they're found, we have the idea that electrons are in energy levels again. Again, looking at low energy levels close to the nucleus, high energy levels further out. So within that energy level, electrons have negative charge. And you can envision that if you brought 2 negative charges together, they're going to repel one another. And so the Pauli exclusion principle helps decide what electrons can do to stay in the same area or region of space outside the nucleus. To overcome that, they have what's called spin. So what we can show, and that's what we're going to do today, is this right here is called orbital notation. The up arrow and down arrow indicate that electrons are spinning in opposite direction, like counterclockwise and clockwise. So you can kind of envision an orbital like a bumper car at a carnival. If you get in the bumper car, let's say you're the driver and you have your friend in the passenger seat. In order for you two to be electrons occupying that same region of space, you would have to sit in the driver's space, turning clockwise, while your friend in the passenger seat is spinning counterclockwise because of charge. The next rule that decides where electrons can go is called Hund's rule. So let's say that the carnival isn't very busy and there's lots of bumper cars available. Well, you and your friend really probably don't want to have to decide who is going to drive. You both probably want to drive the bumper car. And so the idea is electrons are kind of like you and your friend in the bumper car. They want their own bumper car or their own region of space. They don't want to have to share a region of space or bumper car if they don't have to. So what that's showing Hund's rule here is arrows here are representing electrons, and the boxes here are representing regions of space outside of the nucleus. So what we can see is electrons as we add an arrow, again adding an electron, each of these want to occupy their own space. Then, if the electron absolutely has to, it will then share a region of space. So again, just like you and your friends, you all probably want to drive your own bumper car until the bumper cars have run out, and then you'll be a passenger with your friend. And so again, electrons will share space if they have to. And like I said, this will start to make more sense as we do some practice here shortly. So an electron configuration is basically, like I said, like an address to where electrons are found. And there's different parts to an electron configuration, just like you have different parts to your address. So the first thing we have is the energy level, and this is called the principal quantum number. If you guys go on to take AP chemistry, this gets to be a much more deeper topic. We're just kind of skimming the surface when it comes to electrons and really configurations at that. And so there are 7 energy levels at this current point with our current periodic table going to element 118. And so basically, energy levels represent the rings on the Bohr model, where energy level 1 is closest to the nucleus, and energy level 7 is the farthest energy level out from the nucleus. You can kind of think of these like floors in a building, for example. The next piece of the electron configuration, and you saw that in your little cheat sheet, was you were filling in these S, P, Ds, and Fs. So the idea here is that we are writing an electron configuration as an address to where electrons are stored. So S orbitals are this 3-dimensional space in which the electron can be found. The electron is constantly in motion, and so what an orbital does is it just finds the region of space where we think we can find the electron. And so if the electron is stored in an S orbital, it's spherical in shape. So the one thing Bohr did get wrong is that electrons are moving 3-dimensionally. And so you can see here is that we have the X, Y, and Z plane. And so 3-dimensionally, this represents a 3-dimensional sphere. It gets more complex as we move into different types of orbitals describing different regions of space. So I know it's kind of faint because of the ink, but right here we have the p orbital, which takes on what we call a dumbbell shape. And so these are a different orientation on where we have a probability of finding electrons. And so there's 3 different ways to orient that in the X, Y, Z planes. The d orbital kind of takes on a 4-leaf clover appearance for the most part, with the exception of this one here. And then we have electrons stored in an f orbital, which becomes much more complex. So again, what this part of the configuration tells us is basically like, what kind of house do you live in? Do you live in an apartment? Do you live in a townhouse? Those types of things. So this is just showing what region of space do the electrons live in. The last thing that we have, and we're not going to use superscripts today or exponents, we're going to use arrows, but we have to tell how many electrons are in that region of space. So in that S-shaped region, how many electrons are living there, or how many people are living in that home. And so we can do that with superscripts or with a arrow, which we're going to use today. I'm going to skip this analogy and I'm going to skip the rules because I'm going to explain them as I go through the problems on the second page of the notes. So I'm not going to talk too long about those pages there. So we're starting with what's called orbital notation today. So as we build through this, I'm going to show you quicker and easier ways to write configurations, but you have to get this foundation in order for the shortcuts to make sense. So we show an unoccupied orbital just by a line, and then we write the address or the orbital name underneath, and I'll show you that here shortly. So we can have 1 or 2 options in an orbital. We can have 1 electron, or it can have 2. I mentioned that earlier with Pauli exclusion, that electrons have to be spinning opposite of one another. So if an orbital has 1 electron, we show it as an up arrow, or you can show it as a down arrow, but we just show it as 1 arrow for 1 electron. But when you have 2 electrons occupying the same region of space, we show that as an up arrow, down arrow. Notice that I didn't make it a complete arrow. Chemists are lazy, and if we can abbreviate something, we do. So you can show it as a full arrow if you want, but a lot of times we just leave that half part of the arrow off and we show it as kind of a partial arrow. So again, up and down indicates opposite spin, so electrons can occupy a region of space. So let's start taking a look at some practice on what in the world I'm talking about. So you will need a periodic table, and I forgot to mention that at the beginning of the video. So if you have the ability, please pause this and go track down a periodic table. And then again, you definitely want your handy dandy sheet here. Okay. So the first thing you need for writing an electron configuration is you need to know how many electrons an element has. So hydrogen, we're going to say it's neutral. It has 1 electron because its atomic number is 1. So what we're going to do is write the orbital notation to show the address for where electrons are found. So this is what I call kind of like the yellow brick road from the Wizard of Oz. And so the start line is where you always begin with electrons, and we have to store those electrons close to the nucleus, and that starts in that first energy level. So what I have here is 1s. So what I can do is an s orbital, that spherical shaped region, can only hold 2 electrons, and then it's full. It cannot hold more than 2. So we show that as one line. So what I'm going to do here is draw a line. I'm going to label it with the energy level and type 1s. What we then do is we are now going to use arrows to represent those electrons, which we only have 1 electron because it's hydrogen. We're going to show it as an up arrow, and we have now drawn the orbital notation for a hydrogen atom that's neutral. It's going to seem strange. Let's just work through some practice, and then you're going to start picking this up very quickly. So the next one we have is lithium. If you look at your periodic table, lithium's atomic number 3, therefore it has 3 electrons. So what you do here is you go to your start line, you find your energy level. Based on the orbital shape, that decides how many electrons it will hold. So we have 1s, and it can hold 2 electrons. So up arrow, down arrow for opposite spin. Your number of arrows should equal the number of electrons. So we have 3 electrons. So what you do with your yellow brick road sheet here is as you follow through this, you then pick up with your next arrow. So we've followed this line all the way through. So now I'm going to follow here, and that leads me to 2s. I still have the S-shaped orbital, which means it can only hold 2 electrons, which I show as one line. So I leave a little gap in between here. I label this as 2s. It can hold 2 electrons. I only need 1 more to make it lithium. So I'm going to draw just 1 arrow. And that's the orbital notation for lithium. So we're going to build into some more options here. So this next one I have is calcium. Calcium has 20 electrons. And actually looking at my setup here, the next one here is nitrogen, and nitrogen's number 7. So let's go to nitrogen, and then we'll come back to the example with calcium. So in total, we need 7 arrows to show the location for its 7 electrons. So we go to 1s. You'll notice that that is where all of them start. That's filling in that first ring on the Bohr model. We filled that up. We follow our arrow. That takes us to 2s. It's an S shape. It has 1 line. Label it with energy level and type. We are going to fill that up because we need 7 arrows, again, for 7 electrons. So this is where things change. I follow that through, and I've filled that up. I follow on to my next energy level and next region, which is 2p. P can hold 6 electrons, so we represent it with 3 lines. So I have 1, 2, 3. Underneath the middle one, I label it with what it is. And so that was that 4-leaf clover that had 3 different ways to orient in space. So I need 3 more electrons to make this a nitrogen. This is the part where electrons, again, want to spread out as much as possible. So I am not going to pair up electrons. I'm going to have 1 electron take up each region of space. This is what I should not see. So this is incorrect. This is correct. You should space out electrons so they each have their own orbital And again, I now have 7 electrons. We're going to go up to that original example on this particular page with calcium with 20 electrons. Go to start, I go to 1s. Fill that with 2 electrons. Following my map, I go to 2s, put in 2 electrons. Following that map again, we have 2p, which is where we left off with nitrogen. Show it with 3 lines. I will fill this all the way up, so I can go ahead and pair my electrons up, because currently I'm at 2, 4, 6, 8, 10. I have 10 more electrons to get to calcium. So this is where you continue to follow your arrows. That takes you to 3s. The S-shaped orbital can hold 2 electrons. So I'm going to go ahead and do 3s, 1, 2. Following along, I've finished that out. So I follow my next arrow down to 3p. P can hold 6 electrons, so 1, 2, 3. Labeling it underneath. I have 1, 2, 3, 4, 5, and 6. So again, 2, 4, 6, 8, 10, 12, 14, 16, 18. I'm not done. I need 20 electrons. Following 3p, that leads me to 4s. S can hold 2 electrons. So we have 4s, up, down, and we now have calcium's orbital notation. So I'm going to do just one more. We can do the iron one here. And iron, when we look at it, it has 26 electrons. So again, you can see that pattern. We always go to start. All of these S's, doesn't matter if it's 1 or 7s, S will only have one line because it can only hold 2 electrons. Following your map takes you to 2s, followed by 2p. So you can see that because iron only has 6 more electrons than calcium, everything up to that point is going to be the same. Okay, so I'm going to go ahead and keep filling in what I had. So we had 3s, we had 3p, 4s, and again, that's 20 electrons like calcium. We needed to get to 26 electrons, meaning we need 6 more. Where we're at on our map now is here. If we follow it up and follow our arrow, we're now at the orbital 3D, which has more energy than 4s. So some parts start to get out of order, and we're really going to start to make that connection as we make our way into this unit. So D, this is the first time we've used D. It can hold 10 electrons, therefore 5 lines. So we show all 5 lines. Underneath the middle one, label it with the energy level and shape. We need 6 electrons. So I'm going to space them out. So here's 1, 2, 3, 4, 5. Only 1 electron will have to be buddied up. Again, you can always check, did you use all 26? If you count that through, you will count that it has 26 electrons. So that's what you guys are working on, is doing orbital notation. So again, at this point, the big thing I need you to get is the handout here and finding your electrons from your periodic table. If you have more questions, please reach out to me and I will gladly help you out.